Now let's take a problem which is asked in GATE 2003, that is Engineering Mechanics GATE ME 2003. Here I am writing the problem first. A reel of mass m and radius of gyration k is rolling down smoothly from from rest with one end of the thread with one end of the thread of the thread wound on it, held in the ceiling, held in the ceiling, as shown in figure. As shown in figure, consider the thickness of the of the thread and its mass negligible negligible in comparison with radius r of the hub and the real mass m. Take g, which represents acceleration due to gravity. Acceleration due to gravity. Find linear acceleration of reel and tension in the thread. So I am again repeating this problem which is asked in GATE 2003. Here a reel of mass m and radius of gyration k is rolling down smoothly from rest with one end of the thread wound on it. It is held in the ceiling as shown in figure. The thickness and the mass of the thread is negligible in comparison to the radius of the hub and real mass m. We can take g as a acceleration due to gravity, and now we are interested in linear acceleration of the reel and tension in the thread. So first I would like to draw the diagram. This one is the ceiling. Here the thread is attached, and on this thread we are having a reel of mass m, and this distance we are having r. So now this one is the reel, this one is the thread, this one is the thread here, and this one is the radius, that is r. So we will consider two kinds of motion here, linear motion and rotatory motion. So first, for this solution, first consider the linear motion. And for linear motion, let's draw the free body diagram of reel. So here I am drawing the free body diagram of reel. So I am just drawing the free body diagram of the reel here. This thread is attached here, so there will be tension T, and mass will act at the center of gravity, that is mg. So now this thread, if you see, this reel is wound like that and it will move in the downward direction. So the motion direction is like that. So if the body is in motion, then we can easily apply the Newton's second law of motion. That is nothing but net force equals to mass into acceleration. So I can write net force equals to mass into acceleration. I am considering the linear motion, so the acceleration will be linear acceleration. If you see this diagram here, mg is acting in downward direction and t is acting in upward direction, and motion is in downward direction, so the net force in downward will be mg minus t. We know the mass is m, and suppose linear acceleration. So here I will write a is nothing but linear acceleration. Consider the rotational motion. Rotational motion. So for rotational motion, again I will draw the free body diagram of reel. Free body diagram of the reel. And this one is nothing but the t here, and this distance is r, and suppose this point is 4. So for rotational motion means I am considering the rotational motion of reel. So I will interested in torque. So first we will calculate the torque. So torque is nothing but force into perpendicular distance. So here if you see the diagram, force is T and perpendicular distance, that is nothing but R. So torque will be T. We can also apply the Newton's second law of motion for rotatory motion. So here, according to Newton's second law of motion, net torque will be moment of inertia into angular acceleration. Angular acceleration means in case of linear motion we are considering force and we are considering mass and linear acceleration. Similarly, in case of rotatory motion we have to consider torque, and in place of mass we have to consider moment of inertia, and in place of linear acceleration we have to consider angular acceleration. So now we know the torque is T into R here, mass, moment of inertia suppose phi, angular acceleration is alpha. So I can write T equals to I alpha by R. So now we know the relationship between linear acceleration and angular acceleration. So in place of alpha, I can write A by R. So here in place of alpha, I can write A by R. So T equals to IA by R square. So this one is the expression of T in terms of I, A and R. Now we have already mentioned the equation that is nothing but now we are having the equation mg minus t equals to ma. So here I will put the value of t, that is ia divided by r square equals to ma. So now we know the I, that is moment of inertia, is nothing but m into square of the radius of gyration. The problem radius of gyration is k, so I can write mk square a divided by r square equals to ma. So mg will be ma plus mk square a by r square. So mg equals to ma taken common 1 plus k square by r square. So we are interested in a. So a will be g r square divided by k square plus r square. So by this way we can get a linear acceleration a equals to gr square divided by k square plus r square. And now we are interested in t. So we know that t is nothing but ia r square. So if we put the value of I, that is nothing but m a square. Here we can put the value of a, that is g r square divided by k square plus r square, and we are already having r square. So T will be mg k square divided by k square plus r square. By this way, we can also get the value of tension in the thread, that is mg k square divided by k square plus r square. Another great problem which is asked in GATE 2001 Engineering Mechanics, GATE ME 2001. First I will write the problem. In the figure shown, the spring deflects by del to position A, that is equilibrium position, position. When a mass m is kept on it during free vibration, the mass is at position B at some instant. Find change in potential energy of the spring mass system from position A to position B. So let's draw the diagram here. We are having a spring here. The free length of the spring is L. And here we are having the static deflection del and spin constant A. If we put the mass here, then the position will be like that here. And if we go from A to B, here I am having position B, here as A, so this one is X. Now we have to find out that change in potential energy of a spring mass system from position A to B. So let's solve this problem. First, we are interested in potential energy of spring mass system at point A. So here, if you see the length here, the free length is L, and by putting the mass m, it will go to a distance of delta. Means the potential energy will decrease by L minus delta. So potential energy of the spring mass system at that point will be Mg, and height will be L minus G. So this one is the potential energy of the spring at point B. Similarly, potential energy of a spring mass system at point B will be potential energy of mass at B plus elastic potential energy of spring B. So the potential energy of mass at B will be, we are further going at a distance x, so we have to subtract del plus x with L. So the potential energy of mass we can write mg, and we have to subtract del plus x from that is the potential energy for mass. And this spring is compressed by a distance x. So elastic potential energy 1 by 2 k x square. So now we are having mg L minus del plus x plus 1 by 2 k x square. Now we are interested in change in potential energy. So change in potential energy from from position A to B equals to mg L minus x plus 1 by 2 k x square minus of mg L minus del. So we will get minus mgx plus 1 by 2 kx square. So the correct answer is minus mgx plus 1 by 2 kx square. Now let's take another problem which is asked in GATE 1999. Engineering Mechanics GATE AIME 1999. So first I am writing the problem here. As shown in figure, a person A is standing at the center of rotating platform, facing person B, who is riding a bicycle, heading east. The relevant speeds and distance, distances are shown in figure. Person, a bicycle heading east. At that instant, under consideration, what is the apparent velocity of V as seen by A. I will again repeat the question. Here, a person A is standing at a center of rotating platform facing person B who is riding a bicycle heading east. The relevant speeds and distances I will show in the figure. So person, a bicycle heading east. At that instant, under consideration, what will be the apparent velocity of B is seen by A. Means we are interested in velocity of B with respect to A. So what is our interest? Find velocity of B with respect to A. So first I will draw the diagram here. I am drawing the diagram. This one is the rotating platform. Here at the center there is a person A, and here there is a person B who is heading towards east. And velocity is 8 meters per second, and this one is north. And this rotating platform is moving in anticlockwise direction, omega 1 radian per second, and distance between this A and B is 5 meters. Now we are interested in velocity of B with respect to A. So first of all, we are interested in here, we are interested in the angular velocity given, so we are interested in linear velocity. So linear velocity at b due to rotation of platform means we are interested in this velocity. I am drawing here is suppose v. So v, I can write v equals to omega r. So omega we know it is 1 radian per second, and at b r will be 5 meter as mentioned in the problem, that is 5 meter. So v equals to 1 into 5, it will be 5. So 5 meter per second. So this one is the linear velocity at p due to the rotation of platform. Now we are interested in velocity of p with respect to p here. So basically we are interested in velocity of p with respect to a. So we are interested here, that is velocity of b with respect to a. So we are interested in 8 minus p. So if we see the direction here, that is 8 in positive direction. If we see the v, it is in negative direction. So according to the direction, we have to take the proper sign here. So we are interested in velocity of v with respect to a minus v is in opposite direction, so minus v. So v dA equals to 8 plus v. So 8 plus 5 equals to 30 meter. So, and it is coming positive, it means VBA equals to 30 meter second heading east. Heading east. So the correct answer for this problem, the velocity of B with respect to A, 13 meter per second heading east.